Hello. Welcome to lecture 4 on MOSFET operation. Just to give you some overall orientation about where things are going, we're going to be talking about how a MOSFET operates and carries a current. We'll mostly talk about the nMOSFET or nFET. Sometimes you'll hear me say one word to describe it and sometimes another. But the same principles and phenomena apply to a pFET. The only difference about it, and we won't cover it in great detail here, I'll figure out some way as we go along to bring that in and make you more familiar with it, is to remember that whatever I'm talking about in the nMOSFET also applies to the pFET. The only difference is that the diffusion types of the devices switch. Whatever was an N in the nMOSFET becomes a P, and whatever was a P becomes an N. Signs of voltages are also reversed. So positive voltages become negative, and negative voltages become positive. In the nFETs, electrons are the mobile carriers, and in pFETs, holes are the mobile carriers. I want to take you back a little bit to the evolution of the MOSFET. In the early days of semiconductor technology, there was no such thing as a MOSFET. And only later on, as the MOSFET technology developed, did this device emerge. In the early days of semiconductor technology, you would start with two back-to-back reverse bias diodes prior to about 1960. And in this case, if you were trying to measure a current through a meter that I've labeled as IDS on this diagram, you would not see any. There would be no current flowing on the grounded terminal, and there would be no current flowing on the forward bias terminal. So in this particular implementation, there is no current flow. However, the MOSFET technology allowed you to add a gate oxide with a metal contact connected to it. And in that case, a current would be able to flow when, under certain conditions, when an inversion channel is formed by a voltage applied to the gate oxide by the metal. The voltage is applied, the voltage VG is applied to the metal and forms the inversion channel. And that inversion channel can link in a low resistance state the source to the drain, and a current will flow. We're going to try and talk about a MOSFET current model. Some of this will be qualitative in nature, but ultimately we'll get and develop a quantitative model and tailor it to describe the current flow in a MOSFET in two regions. The linear regime, where the drain voltage, one of the voltages applied to the drain of the device, and we'll talk about that later, is very much less than the voltage applied at the gate and the threshold voltage. For now, let's just say that the threshold voltage is the onset voltage at which current begins to flow. During this, in the linear regime, the channel resistance doesn't change as the voltage applied to the drain increases. In the saturation regime, where the drain voltage is comparable to the difference between gate voltage and the threshold voltage, the channel voltage changes as VD increases. We'll talk about that in more detail as we go along and add some understanding to it. This diagram shows the regions of the MOSFET current. In this case, in cases where the gate voltage, which is applied up in here, is greater than the threshold voltage, the inversion layer will form and a current will be carried between the source and drain voltages in the device. When a larger drain voltages are applied, again, as long as the gate voltage is greater than the threshold voltage, an inversion channel will form. But in this case, the drain voltage will decrease the surface field that is formed in the inversion layer, and the inversion layer will narrow as it approaches the drain. And finally, when the drain voltage becomes very, very large compared to the saturation voltage, the inversion layer will stop midway somewhere in the device and will still conduct current, but it will eventually shut down or will not increase as the drain voltage increases. That's all of those current regions are depicted in the drain versus VDS voltage graphs that I show below. In the linear region, the drain voltage increases linearly with the drain to source voltage that is applied. In the at the onset of saturation, when the inversion layer begins to narrow to zero in the channel of the device, there will be a saturation voltage that is reached at something called the saturation current. Finally, in the saturation current, the drain voltage will, after it reaches the saturation onset point, will level out to a value and not increase, even though the drain to source voltage is increasing there. We'll talk about this again as we go on later and give a more physical explanation of why that happens. This is an example of a MOSFET, a measured MOSFET current characteristic. And as you can see, this is the linear region up in here. And in the early portions, it's very much linear. It will increase along these curves as it goes along. As the drain voltage increases beyond that point, it starts curving over because of something, because of some narrowing that is occurring in the drain voltage. In the inversion channel as the device is as the drain current is increased. And finally, at very large drain voltages, you can see that the current remains constant throughout the whole operation of the device. And again, that happens again because of the region where the device is approaching something called pinch off.